Welcome everyone. I'm Robert Riedel, CEO and co-founder of Class 5 Photonics, and today I'm glad to present you our recently developed high repetition rate extreme ultraviolet source and Terahertz driver laser. This work has been performed in cooperation with the Helmholtz-Zentrum Dresden-Rossendorf, the group of Jan Deinert. So Class 5 Photonics delivers ultra-fast, high-power laser technology based on robust optical parametric chirp pulse amplifiers, OPCPA, hence providing high-power, tunable femtosecond pulses at user-friendly operation. We serve a wide range of applications from bioimaging to ultra-fast material science, attosecond science, and EUV soft X-ray. Today's topic combines our high-power OPCPA systems for ultra-fast science with our most recent high harmonics generation source to enable advanced material studies with Terahertz pump and EUV probe beams. Let's have a brief look into this application. Angular resolved photoemission spectroscopy, for example, is a technique that allows resolving the electronic band structure of solids. A trend in this field is now to trigger the electron dynamics using a long wavelength driver in the terahertz range, for example. And then, after triggering the dynamics, to probe it with EUV photons to photoexcite electrons with access to the full Brillouin zone because of the high photon energy. I will show you a schematic of such an experiment. We see our familiar scheme again. So we have the optical pump or terahertz pump and the XUV probe. The terahertz pump can be generated by the so-called optical parametric optical rectification, a second-order nonlinear effect, and the EUV pulse can be generated via a high harmonic generation source. At Class 5 Photonics, we designed a system that is optimized for such a pump probe scheme using all the benefits of OPCPA technology. First of all, we have a 350 watt ytterbium YAG InnoSlab laser that is being used as a pump. It provides 1 micron wavelengths and 2 millijoules of this laser at 600 femtoseconds serve as the ideal driver for this optical rectification. Secondly, we have our white dwarf HE OPCPA at 800 nanometers to drive the high harmonic generation source with about 10 watts of average power at ultra-short pulse duration. And so we are able to address 21 to 50 electron volts of photon energy at 100 kilohertz repetition rates. In the following, I will guide you through the laser system, beginning with a more detailed schematic, measurements results of the OPCPA, and finally, high harmonic generation results. So this is the schematic of the OPCPA laser system. What we have here is the ytterbium YAG pump laser again, 1 micron, 3.5 millijoules in total, 100 kilohertz, so that adds up to 350 watts at 600 femtoseconds. Part of that power, as explained earlier, is directly directed out to the terahertz generation that is provided by the user. Then we have the main HHG driver, which is our white dwarf HE OPCPA. So for this system, we split part of the energy for white light generation to have a broadband seed. We stretch in the bulk sapphire, amplify in 2 subsequent optical parametric amplifiers, and then we finally compress in a chirp mirror compressor. After that compression, we generate a second harmonic, potentially, and then we focus those pulses into the high harmonics generation source. So for further capabilities of the system, there's also a tunable OPA that provides a fraction of the power, but that one can run in parallel and provides visible and UV outputs also for probing or pumping at different wavelengths, which makes the system quite flexible for a wide range of materials to be studied. I suggest we have a first look on the pump laser itself. So it's an ytterbium YAG InnoSlab at 350 watts, and some of the main specs are shown here. We have the autocorrelation that shows 579 femtoseconds and a very nice pulse contrast. And one important fact for OPCPA, especially for higher energy OPCPAs, is the near field beam quality. So we have measured here the collimated beam at 3 different positions, 1.2 meters after the amplifier, 1.8 meters and 3 meters to ensure homogeneous beam profile of that pump system. The beam quality has also been measured, revealing 1.2 and 1.04. That laser is very stable in output power. As you can see here, this is a 10-hour plot measuring a warm-up curve. And as you can see here, we see an average power of 354.6 watts with a standard deviation of 0.7 watts that corresponds to 0.2%. The pulse-to-pulse energy stability has also been measured with a fast oscilloscope to be slightly below 1%. So the OPCPA output itself, so this is the main output that is also being used to drive the HHG. We can design OPCPA in a way that we get a very nice, very clean pulse, as you can see from the autocorrelation trace here. So this pulse has artificially been designed for sub 40 femtoseconds pulse duration, Fourier limited, in order to restrict the bandwidth of the harmonics generation later to sub 100 millieV. And here you can see a spectrum centered around 800 nanometers with the corresponding spectral bandwidth. Also, the OPCPA can be operated in a very stable fashion. So this is a plot that shows almost 50 hours of continuous operation with an average output power of 10.8 watts, also at the standard deviation of 0.7%. And the output beam profile is quite decent. The measured corresponding beam quality is m square of around 1.3, 1.4. So this is being used for harmonics generation by 800 nanometers, but we also want to generate quite low harmonics of 21 electron volts. And for that application, we need to generate the second harmonic. So we use this pulse here, this 800 nanometer pulse, to generate the second harmonic. And you can see here an overview of the results. So this is basically the spectrum centered at 400 nanometers. And also here the stability here measured over 16 hours is 0.7%, and we have about 50% something like 40% conversion efficiency for what's here for the output. Now for OPCPA 3, for output 3, we have a little overview just about the tunability. I don't want to go too much into detail, but it can basically be tuned from about 700 to 950 nanometers. The spectral bandwidth corresponds to about sub 30 femtoseconds here throughout the whole range, which is very nice. So you always get a short pulse. And we can generate also the second harmonic here in a tunable fashion, and also the third harmonic to address a quite wide wavelength range at quite high power levels. Let's use the final minute to discuss about the high harmonics generation source itself. As mentioned in some of our earlier works, we are following design of Hewan from Berkeley National Lab. So here you see basically the schematic, and on the left side you see our Moonlander HHG 50, which is our commercial HHG source. And as you can see, we enter the setup with the 800 nanometer beam. We generate the second harmonic in a beta barium borate BBO crystal, and then we filter with dispersion optimized dichroic mirrors. And finally, we focus this blue beam into a gas cell, which is located in the HHG chamber. Afterwards, we have to filter out to block the infrared beam, or the blue beam in this case, with an aluminum filter. Afterwards, we apply a bandpass filter that is a tin metal filter. And behind the tin metal filter, we can measure the energy of the generated harmonics with a EUV photodiode. So The results can be shown, can be summarized here. You see on the left side the tin filter transmission. It transmits only one harmonic, which is the 7th harmonic of 400 nanometers at about 21.7 eV. The pulse duration is expected to be sub 30 femtoseconds in this case. And the photon flux that we measure with the EUV diode behind this filter can be calculated back to a source flux of 10 to the 13 or more than 10 to the 13 photons per second. So in this configuration, the OPCPA, the HHG source can provide single line high flux 21.7 eV, for example, for ARPES, but we can do way more, right? So for a different configuration, we equipped the laser system with a 25 femtosecond driver mode at about 80 microjoules pulse energy, 800 nanometer central wavelengths. And you can see here a spectrum, a measured spectrum of this wavelength range with a corresponding photon flux of each individual harmonic after the filtering. So this is the direct signal on the diode. So we have 3 times 10 to the 12 photons per second, and in this case a peak of 1.4 times 10 to the 12 photons per second at about 38 electron volts. And now by tuning the central wavelengths, we are even able to tune those harmonics. So this is ongoing work that will be hopefully presented soon. In addition to that, we can also tune the gas pressure to optimize, for instance, a phase matching here at 30 eV over 38 eV. And you can see here we have a cutoff for this operation regime that is at about 50 electron volts and still giving 1.4 times 10 to the 11 photons per second. With those results, I would like to thank you. I presented an OPCPA pump probe suite, a Terahertz pump EUV probe with a high flux at 100 kilohertz, 10 to the 13 photons per second in the energy range 21 to 50 eV, and the system is specially designed for ARPES and coherent diffractive imaging. And so on behalf of the Class 5 team, I would like to thank you for your attention.